Bismillahirrahmanirrahim. We are going to start the dynamic equation of gradually varied flow, which is also known as the gradually varied flow equation. Actually, the topic which we are going to study is the water surface profiles. What are the water surface profiles, how the water surface profiles are drawn, and what is the importance of the water surface profiles. In order to discuss the water surface profiles, we are going to understand and derive this equation, which is known as the dynamic equation of gradually varied flow. This equation is used to compute the water surface profiles. So you can see that again I have drawn a figure for a non-uniform flow where S naught is the slope of the channel bed, this is the slope of the water surface, and this is the slope of the energy line. You can see that Y1 is greater than Y2, showing that the flow is non-uniform. This is Z1, Y1, and velocity head and velocity head, and H1 is the total head at section 1, 1. Similarly, H2 is the total head at section 2, 2, and head loss. Head loss is denoted by DH, where DH is the difference between the two heads. Of course, the difference between the two heads is actually the total head. Okay, so this is all about the figure. Now what we are going to do, we will say that total head is equal to Z plus Y plus square of V divided by 2G, and then we will take the derivative of this. Okay, you can see here V is equal to Q. I have put the value of V is equal to Q divided by Y, means we are going to derive equation for a rectangular channel. Okay, this equation is valid for the rectangular channel which we are going to derive, and you can see that I have taken a derivative with respect to x, and when you will take the derivative and you will simplify the equation, you will get this result: dy by dx is equal to s naught minus s divided by 1 minus square of the fruit number. You can check the derivation by yourself. It is a very simple and easy derivation, but in case of any problem we can discuss it in the next class. आप इसको check कर लें, कोई problem हो तो फिर मुझसे next class में पूछ सकते हैं. But it's a very simple derivation, and the result is this, that dy by dx is equal to s naught minus s divided by 1 minus square of the fruit number, where s naught is the slope of the channel bed and s is the slope of the energy line. Okay, we can also say that S is the slope of the energy line and S naught is the slope for the uniform flow. Okay, S is the slope of the energy line for non-uniform flow, and S naught is the slope of the energy line for uniform flow, because we know that for uniform flow, slope of the energy line, slope of the channel bed, and slope of the water surface, all the three slopes are equal to each other. So you can say that S naught is the slope of the channel bed, or you can even say that S naught is the slope of the energy line for uniform flow. Okay, and what is this? Dy by dx. Y is the depth of the flow and x is the horizontal distance. So this equation will show you that what is the change in the depth of the flow with respect to the horizontal distance. Okay, and this is how you will be able to draw the flow profile. Flow profile का क्या मतलब होता है? आपने फ्लो प्रोफाइल का ये मतलब होता है कि आपने मतलब बताना होता है कि डेप्थ ऑफ द फ्लो, ये अभी हम डिस्कस करेंगे तो आपको समझ भी आएगी कि व्हाट इज द डेप्थ ऑफ द फ्लो एट दिस पर्टिकुलर डिस्टेंस. So you will be able to compute and you will be able to draw the profile with the help of this equation. Then we will discuss the flow zones. A flow can be divided into 3 zones, and these zones are separated by slope of the channel bed, critical depth line denoted by CDL, and normal depth line denoted by NDL. Okay, so let's take an example of the mild slope. For a mild slope, let's suppose this is a mild slope where S naught is the slope of the channel bed, and we know that the mild slope is the slope where we have a kind of subcritical flow. Means the on a mild slope, the normal depth of flow is always greater than the critical depth of the flow. ठीक है, ये चीजें हम स्टार्ट की क्लास में डिस्कस कर चुके हैं. The normal depth of the flow is always greater than the critical depth of the flow on the mild slope. Therefore, you can see here, you can also see that normal depth of the flow is greater than the critical depth, and that's why normal depth line is above the critical depth line. Okay, first of all, you will draw this slope of the channel bed. Above the slope of the channel bed will be a critical depth line, and above the critical depth line will be a normal depth line. If you are going to draw a figure for the steep slope, then what you will do, we know that for the steep slope, the critical depth of the flow is greater than the normal depth of the flow. Therefore, first of all, you will draw slope of the channel bed, then you will draw normal depth line, and then you will draw the critical depth line. I'm talking about the steep slope. Okay, so you have to remember and you must know that what is the situation of the y0 and yc, and according to that situation on that particular slope, you will be able to draw the critical depth line and normal depth line. Well, this is a figure for mild slope, and it is written here that S0 is less than SC. This is also what we have already discussed in one of our previous classes, that what is the critical slope? SC is the critical slope. Critical slope is defined as the slope where the flow is uniform but undisturbed, and that flow is also known as the critical flow. Okay, on a critical slope, the flow is uniform as well as critical, and if the slope gets smaller than the critical slope, then what happens? The depth of the flow increases, and that slope is known as the mild slope. But if the slope of the channel bed is greater than the critical slope, then what happens? The velocity of the flow increases and the depth of the flow decreases, and that is known as the steep slope. So you can say that critical slope is a kind of a benchmark with the help of which we decide whether the slope is mild or the slope is steep. Okay, so here you can see that this is the mild slope, where this is the slope of the channel bed, then critical depth line, then normal depth line. This is the normal depth of the flow, this is the critical depth of the flow. Now suppose that we have this situation of the flow. This is the flow, and which is denoted by y1. Now if the flow is here above the normal depth line, we will say that the flow in zone number 1, and we will say that in this zone y1 is greater than y0, which is greater than yc. Okay, we will say that the flow is in zone number 1, and we will represent this flow by m1, where m stands for mild slope, because we are going to discuss the case of the mild slope. So m is the mild slope, and 1 means it is in zone number 1. Okay, now forget about y1. Let's suppose the flow is here between the normal depth line and the critical depth line. If the flow is here, we will say that the flow is in zone number 2, and where y0 is greater than y2, which is greater than yc. Okay, and the flow in this zone will be denoted by m2, where m stands for the mild slope and 2 stands for zone number 2. Similarly, if the flow is here below the critical depth line, then we will say that it is zone number 3. In this case, we will say that y0 is greater than yc, which is greater than y3. Okay, and it is denoted by m3, where m stands for mild slope and 3 stands for zone number 3. Okay, It can also be defined as this. How zone number 1 is defined? You can see that normal situation of normal depth line and critical depth line is different for different types of the slopes. Therefore, zone number 1 is defined as the space above the upper line. Okay, this is the upper line, this is the lower line, and this is the slope of the channel bed. So what is zone number 1? Zone number 1 is the space above the upper line. Zone number 2 is the space between the two lines. Okay, what are the two lines? The critical depth line and normal depth line. And what is zone number 3? This is the space below the lower line. Okay, slope of the channel bed is not a line, this is the slope, and these are the lines. So zone number 1 is the space above the upper line, zone number 2 is the space between the two lines, and zone number 3 is the space below the lower line. So this is all about the zones of the flow, and remember, we are going to discuss all these things to draw the flow profiles. The last topic of this lecture will be flow profile, how to draw the flow profile, and then we will use the knowledge of all these things. So this is all about this, which we have already discussed. Okay, let's now take an example of the steep slope. We know that steep slope is always greater than the critical slope. That's why on a steep slope, the velocity is higher and the depth of the flow is smaller. So here you can see that the depth of the flow, the normal depth of the flow is smaller than the critical depth of the flow, and that's why on the steep slope, critical depth line is above the normal depth line. Okay, so in this case, what will happen if the flow is here in zone number 1, okay, and we will denote the flow by y. So we will say that y is greater than yc, which is greater than y naught. It is written here also. You can see y is greater than yc, which is greater than y naught, and the flow in zone number 1 will be denoted by S1, where S where S stands for the steep slope and 1 stands for zone number 1. Okay. Similarly, if the flow is in zone number 2, then the flow will be here in zone number 2. Then you will say that YC is greater than Y, which is greater than Y naught. Here you can see YC is greater than Y, which is greater than Y naught. And the flow will be denoted by S2, where S stands for the steep slope and 2 stands for zone number 2. Similarly, here in zone number 3, if the flow is here in zone number 3, we will say that YC is greater than Y naught, which is greater than Y, and the flow profile will be denoted by S3. So in this way, you can define all kinds of the slopes, and you can define all kinds of the flow in different kinds of the zones. Okay, this is an example of the critical slope. We know that the critical slope is the slope where you have to write it as yc is equal to y naught, because the critical slope is the slope where the flow is always normal, and that normal flow is known as the critical flow. Okay, आपने इसको लिखना है yc is equal to y naught. Remember, the depth of the flow on the critical slope is denoted by yc, which is actually y naught. Okay, in this case, we have this line, which is the critical depth line as well as normal depth line. यहाँ पर भी मुझसे गलती हुई है, आप इसको critical depth line slash normal depth line कर दें, ठीक है, और इसको yc is equal to y naught कर दें. Okay, in this case, you can see that this critical depth line is the line which is the normal depth line also. Or you can say that critical depth line and normal depth line coincide with each other. So we have only two types of the zones now, zone number 1 and zone number 3. There is no zone number 2. Why? Because we have already discussed that zone number 1 is the zone above the upper line. Zone number 2 is the space between the two lines. So here the two lines coincide with each other, therefore there is no zone number 2. And zone number 3 is the space below the lower line. So we have zone number 1 and zone number 3. Zone number 2 is missing here, and so we have two kinds of the flow profiles in critical slope. If the flow is in zone number 1, we will say that y is greater than yc, and we will denote it by C1. Okay, where C stands for critical slope and 1 stands for zone number 1. And if the flow is here, we will say that YC is greater than Y, and it will be denoted by C3, where C stands for the critical slope and 3 stands for the zone number 3. In this way, you can also define the horizontal slope and the adverse slope. When we will discuss the flow profiles, we will discuss the horizontal and adverse slope also. What are the horizontal and the adverse slopes? For horizontal slope, we say that the slope is equal to 0. And what is the adverse slope? Adverse slope is the slope for which we say that the slope is less than 0, means we have a negative value for the adverse slope. Okay, when we will discuss, you will come to know that how we get negative value for the adverse slope. So let's come to our topic, water surface profiles in gradually varied flow. What's a water surface profile? The water profile represents the surface curve of the flow. What kind of a curve is made by the flow, that is known as the flow profile or the water profile. Remember, there are two types of the curves. One is known as the backwater curve and other is known as the drawdown curve. What's the difference between these two? Backwater curve is mostly found in case of an obstruction in a channel. For example, if you have any kind of hump on a channel, let's suppose you have a weir or you have a dam, then what will happen? Behind the dam or behind any kind of hump, when water will approach that hump, what will happen? The level of water will be increased. Okay, the depth of the flow will be increased. That kind of a curve made by water is known as a backwater curve, where we say that the depth of the flow increases in the direction of the flow. Or you can say that the depth of the flow increases at the downstream side. Okay, in case of the dam, when you look behind the dam, what will be happening? The depth of the flow at the upstream will be smaller than the depth of the flow at the downstream. And why? This is because of the obstruction in a channel. That kind of the curve is known as a backwater curve. And what's the drawdown curve? This is a very simple and general situation where the depth of the flow decreases at the downstream side. Okay, this is the simple situation where the depth of the flow is greater at the upstream side and smaller at the downstream side. And how we will come to know whether the flow, whether the curve is a backwater curve or a drawdown curve, with the help of this equation which we have derived at the start of this class. This is the dynamic equation of gradually varied flow. We will put values in this equation, and if we get a positive value, it means that the flow is a backwater curve, and if we get a negative value, it means that the profile is actually a drawdown curve. Okay, so you have to remember it: positive for the backwater curve and negative for the drawdown curve. And what will be the kind of the curve? Let's suppose this is a y-axis. Okay, this is a y-axis and this is x-axis. X-axis is actually a normal depth line. And what will be the kind of a backwater curve? This is a backwater curve, you can see. Okay, this is a backwater curve. This is upstream side and this is the downstream side, and you can see that the depth of the flow is increasing at the downstream side. So this kind of there may be a dam or weir here. That's why the depth of the flow is increasing. So this kind of a curve is known as a backwater curve. Okay, and you can see this is a drawdown curve. Okay, this is a drawdown curve. You can see if the slope of the channel bed is here. ठीक है, यहाँ पर आपके पास slope होगा, ये आपके channel bed का slope है, and you can see that here the depth of the flow is this much higher. Here the depth of the flow is smaller, and here the depth of the flow is very, very small. Okay, so this is known as a drawdown curve because the depth of the flow is decreasing towards the downstream side. These are the back shapes of the backwater curve and the drawdown curve with respect to the normal depth line. And remember that when you will draw the backwater curve and drawdown curve with respect to normal depth line, they will be tangent. You can see in starting, the curves are tangent to the normal depth line. Okay, this curve is also tangent to the normal depth line. So these are the important shapes which you have to remember. That what is the shape of the backwater curve and drawdown curve for normal depth line, and you should remember that these curves are actually tangent to the normal depth line. Okay, this is another shape for the backwater curve and the drawdown curve with respect to the critical depth line. Okay, here again we have a y-axis and x-axis, but here x-axis is actually a critical depth line, and you can see that we have drawn backwater curve and drawdown curve, and you can see that okay, now this is a backwater curve. Again you can see that the depth of flow is increasing towards the downstream side, and this is the drawdown curve where the depth of flow is decreasing towards the downstream side. And where is the slope of the channel bed? You can draw the slope of the channel bed here. ठीक है, यहाँ पर आप slope of the channel bed की एक line draw कर लें तो आपको ज्यादा clear हो जाएगा. You will be able to know that for a drawdown curve, you will be able to know that this is the starting depth of the flow. Let's suppose y1, and this is the y2, and you will be able to know that y1 is greater than y2. Similarly, अगर आपने backwater curve को check करना है, तो आप यहाँ से एक line draw करें, ठीक है, y1 की. आप यहाँ से आएंगे slope of the channel bed तक, you will say that this is y1. फिर आप यहाँ से आए, you will say that this is y2, and you will be able to know that y2 is greater than y1 because this is a backwater curve. Okay, important thing is this, that the backwater curve and the drawdown curve, okay, forget about these dotted lines. You can see that what's the backwater curve? The backwater curve joins the y-axis, and then it is perpendicular to the critical depth line. Similarly, if we talk about drawdown curve, it meets the y-axis, and then it is perpendicular to the critical depth line. Okay, but it is not actually perpendicular. We can join them like this by the dotted lines. This is actually a kind of the rapidly varied flow which is not defined by the gradually varied flow equation. We are going to draw these curves on the basis of the gradually varied flow equation, and gradually varied flow equation cannot define the rapidly varied flow. This is a rapidly varied flow part which is not defined by the gradually varied flow equation, so we can join the two curves by this kind of the dotted line. Okay, so you have to remember that what's the shape of the drawdown curve and backwater curve when they are with the normal depth line. Remember that the two lines are tangent, and these are the shapes of the backwater curve and drawdown curve when you are going to draw with respect to the critical depth line, and remember that they are perpendicular to the critical depth line. Okay. Now we will examine the gradually varied flow equation. Remember that we are going to draw and discuss the flow profiles qualitatively. Okay, we are not going to discuss it quantitatively, means we are not going to put the value of each and every parameter in this equation. Actual situation is this: you must know the value of S0, you must know the value of S and Prude number, put the value, find the value of dy by dx numerically, and draw the flow profiles. But here we are just going to examine that what will be the shape of the profile. Therefore we are just going to discuss it qualitatively. So this is the equation with the help of which we can draw the flow profiles, because this is the equation which will decide whether the flow will be a backwater curve or a drawdown curve, and then we will be able to draw the flow profile for a particular slope. So first of all, we will examine the numerator of the equation, and then we will discuss the denominator of the equation. Here you can see that we have two, in the numerator we have two parameters, S naught and S, where S naught is, you can say that this is the slope of the channel bed, or you can say that this is the slope of the energy line for uniform flow, and this is the slope of the energy line for non-uniform flow. Okay, S naught and S. In order to compare S naught and S, we will compare Y naught and Y. Y naught is the normal depth of the flow, and Y is the depth of the flow. ओके, एस नॉट और एस को कंपेयर करने के लिए आपने क्या करना होगा, आपने y और y नॉट को कंपेयर करना होगा. Okay, now we can discuss the meaning equation. In order to compare these equations, you can see that according to meaning equation, v is equal to 1 by n, r 2 by 3, s 1 by 2. This is the equation for the non-uniform flow. And you can see that if we say that r is equal to y, hydraulic radius is equal to y for very wide rectangular channel, and putting the value of r is equal to y, then putting value of v is equal to q divided by y, because we are going to discuss wide rectangular channel, you will be able to derive this equation that s is equal to square of q into square of n divided by y power 10 by 3. Similarly, you will get the value for S naught, that is equal to Q naught square into square of n divided by Y naught power 10 by 3. Now we will assume that the unit discharge and meaning roughness coefficient is constant for the whole channel. So if you divide these two equations, S divided by S naught, then it will be equal to y naught divided by y power 10 by 3. From this equation, you can see that slope of the energy line and depth of the flow have a kind of inverse relationship with each other. Okay, greater the slope, smaller will be the depth of the flow. Again, smaller the slope, greater will be the depth of the flow. So remember that slope of the energy line and the depth of the flow have inverse relationship with each other. So using this equation, or using this knowledge, now we can compare this S naught and S. So what we are going to do, you can see that numerator contains S naught and S, thus we will compare Y naught and Y. Okay, so what we will say that if Y, what is the Y? Y is the depth of the flow in any zone, which we have already discussed. Y can be a flow in zone number 1, or it can be a flow in zone number 2, or it can be a flow in zone number 3. Okay, so you have to examine Y, where your Y exists. If Y is greater than Y naught, then what we will say, S is less than S naught, because we have already derived that Y and S have inverse relationship. So if Y is greater than Y naught, S is less than S naught. And in this equation, if S is less than S naught, you will get a positive value for the numerator. Okay. Similarly, you will say that if Y is smaller than Y naught, then according to the meaning equation, S will be greater than S naught, and if S is greater than S naught, you will get a negative value for the numerator. Okay, so this is all about the value, the signs for the numerator, and now we will examine the denominator. In denominator, what we have, 1 minus the square of the Froude number. What's the Froude number? Froude number is related to the critical flow. Okay, so for the denominator, we will compare Y with YC. Okay, for the numerator, we have compared y with y naught, and for denominator, we will compare y with yc. Why? Because here we have a fruit number. So we will say that if, okay, we will say that if y is greater than yc. Now you can see that this is the situation for the subcritical flow. If y is greater than yc, then fruit number will be less than 1 and we will get a positive value. You can see if fruit number is less than 1, here if fruit number, the value of fruit number is less than 1, then 1 minus that number and you will get a positive value. So you will get a positive value for the denominator, and if y is less than yc, then you will get a situation of the supercritical flow, and for which fruit number is greater than 1 and you will get a negative value for the denominator. This is how you can examine the equation, the gradually varied flow equation without putting values. You can find whether you are going to get a positive value or you are going to get a negative value for the equation. Okay, let's now examine the mild slope. Again, we have taken an example of mild slope first. Here you have a slope of the channel bed, then you have a critical depth line, then you have a normal depth line. This is y naught and this is yc. Okay, if the flow is in zone number 1 here, then what will be the situation? You will say that y is greater than y naught, flow is here. So y is greater than y naught, which is greater than yc. Okay, and we want to check the values in the zones. Okay, what's the value of dy by dx, whether we are going to get a positive value or a negative value. So I have already told you that you have to come, for the numerator of the equation, you have to compare y and y naught, and for the denominator, you have to compare y and yc. So first of all, we'll compare y and y naught. Y is greater than y naught, and thus according to Manning equation, s is less than s naught, and thus we are going to get a positive value. Okay. Similarly, for the denominator, we will say that y, here you can see that y is greater than yc, a subcritical flow. Therefore, fruit number is less than 1, and again we will get a positive value for the denominator. So in zone number 1, dy by dx is equal to plus divided by plus is equal to plus. Means we have a positive value of dy by dx in zone number 1, and thus we are going to have a backwater curve when the flow is in zone number 1 on a mild slope. And this is the situation which never changes. Whenever on a mild slope the flow is in zone number 1, you will always get a backwater curve. Similarly, if the flow is in zone number 2, then what will be the situation? You can see that this is the situation that y naught is greater than y, which is greater than yc. Comparing the numerator and denominator, for numerator we will say that y naught is greater than y, and thus s naught is less than s. And if you can see, if s naught is less than s, now you can see at the equation, you can look at this equation, s naught is smaller than the s. So what you will get? You will get a negative value here for the numerator. Okay, so you will get a negative value for the numerator here. And if y is greater than yc, again it's a subcritical flow, fruit number is less than 1, and thus you will get a positive value. So in zone number 2, negative divided by positive is equal to negative value. So you will get a negative value in zone number 2, means there will be a drawdown curve in zone number 2. The depth of the flow will be decreasing here in the drawdown, and the flow will, the profile will be a drawdown curve. Similarly, for zone number 3, you will draw a flow profile, and you will say that y naught is greater than yc, which is greater than y. And then you will compare y naught and y. First, you can see that y naught is greater than y. Therefore, S naught is less than SC, and you will get a negative value for the numerator of the equation. And here YC is greater than Y, Froude number is greater than 1, and you will get a negative value for the denominator. And it shows that dy by dx is equal to negative divided by negative is equal to positive value. So again, you are going to have a backwater curve in zone number 3 of the mild slope. Okay, so this is how you can find whether you are going to have a backwater curve or drawdown curve in a particular zone on a particular slope, and you can draw the flow profiles. Now you can see that I have drawn these flow profiles for the mild slope. This is the mild slope, this is the critical depth line, normal depth line, and we know that dy by dx is equal to plus, minus, and plus. So here we have to draw, first of all, look at zone number 1. Here we have a positive value, which shows that we have to draw a backwater curve. Okay, and we know that the backwater curve with respect to the normal depth line is tangent to the normal depth line. Okay, this is what we have already discussed, that when we will draw the curve with respect to the normal depth line, the curves will be tangent to the normal depth line and perpendicular to the critical depth line. So you can see that here, and here this curve, the backwater curve, is tangent to the normal depth line, and here we have a drawdown curve which is also tangent to the normal depth line. Okay, and okay, now this is a curve which is tangent to the normal depth line, and when it comes to the critical depth line, it becomes perpendicular. Okay, and similarly here in zone number 3 we have again a backwater curve. You can see that this is a backwater curve which is perpendicular to the critical depth line. This is the slope of the channel bed. You can check all the curves. Okay, this is M1, this is M2, this is M3, and you can check all of them. First of all, if you want to check this curve, which is a backwater curve, you can see that this is the slope of the channel bed. Here you have this depth of the flow Y1, and here this is the depth of the flow Y2. So you can see that in zone number 3 the depth of the flow is increasing. Similarly, if you want to check M2 curve, which is a drawdown curve, you can draw the flow depth here. If you draw the flow depth, this is Y1, okay, with respect to the slope of the channel bed, and this is Y2, and of course Y2 is smaller than Y1, showing that this is a drawdown curve, or the flow is decreasing in the direction of the flow. So this is all about, you can see, okay, here you can see that M1 and M2 are tangent to the normal depth line, where M2 and M3 are perpendicular to the critical depth line. So you have to keep in mind there are two important things. What is the value of dy by dx, which will show you whether you are going to draw a backwater curve or a drawdown curve. And second important thing is to remember that curves are tangent to the normal depth line and perpendicular to the critical depth line. So this is how you can draw the flow profile for all kind of the slope, for the steep slope, for the critical slope, and all kinds of the slope. Okay, these are the slopes with their practical applications. I have taken this figure from Google, but this is the same figure as in your Franzini book. I think this is on your page. This is on page number 373 of your Franzini book, if I'm not wrong. So you can check these similar figures in your Franzini book also, and I will recommend to search it on Google, and you will get much more examples and you will be more clear. So you can see that again this is an example of a mild slope, and I have drawn the same curves above. This is M1, M2, and M3. This is a backwater curve, M2 is a drawdown curve, and M3 is again a backwater curve. So what's the practical examples? You will get M1 curve in open channel when you have any obstruction on the channel. You can see that this is a dam or a weir on a channel, and what is happening when water is approaching the obstruction, you can see that the depth of the flow is increasing. Okay, so this kind of curve is found on a mild slope, and one is found on a mild slope when you have any obstruction, any hump on a channel. M2 curve is fine when you have this kind of a brink, or you can say a waterfall. Okay, this is known as a brink or a waterfall. When water will fall through the brink, then you will get M2 curve. You can see that the depth of flow is decreasing towards the downstream side. And if you have, this is third example, if you have a sluice gate on a mild slope, then what will happen? You can see that sluice gate also act as an obstruction in a channel. So first of all, the depth of the flow will be increasing behind the sluice, and you will get M1 curve like this, where the depth of the flow increases. And then under the sluice gate, the depth of the flow will be again increasing. You will get M3 curve, and after hydraulic jump, the flow will become normal. Okay, so you have an example of M1 and M3 in this case. Okay, in the case of the sluice gate, and here we have an example of M2, and here we have an example of M1. Similarly, if you look at the steep slope, for the steep slope, we have a backwater curve, and then a drawdown curve, and then a backwater curve. But here you can see that this is a critical depth line. So the backwater curve and the drawdown curve are perpendicular to the critical depth line, and here you can see that they are tangent to the normal depth line. Okay, and these are the practical examples of the steep slope. You can see again we have a hump on the open channel, and what will happen when a high speed flow will approach the hump, the hydraulic jump will create, and after that the depth of the flow will be increased, and we will get this kind of the curve, which is known as S1. You can see that this is the backwater curve, and you can see the difference. What kind of curve is formed on a steep slope when it approaches the obstruction, and what kind of curve is found on a mild slope when it approaches any obstruction on the channel. So these are the differences. You can also see that here there's no hydraulic jump because the depth of the flow is already higher, and it gets a little higher when it approaches the obstruction. But here the depth of the flow is very, very small, so when it approaches an obstruction, then first of all hydraulic jump is created, and then the depth of the flow is increased. Here you can see that we have this kind of the channel. Here we have this kind of the situation where the channel is like this. Okay, this is non-uniformity in a channel, and you can see again that first of all what will happen, this is a kind of obstruction in a channel, and this obstruction is due to the bed of the channel. And you can see again we have hydraulic jump, and after which we have S1 curve, and then it changes into S2 curve, means a drawdown curve, which is shown here also, and then the flow will become normal. And in example of S3 curve, if you have sluice gate on the steep slope, again you have S1 curve behind the sluice gate, and below the sluice gate you will get S3 curve, which will gently changes into the normal depth of the flow. There's no hydraulic jump under the sluice gate in case of the steep slope. You can see here under the sluice gate we have hydraulic jump, and here we have no hydraulic jump. There is a gentle variation in the depth of the flow under the sluice gate. Here we have an example of the critical slope. I already told you that for critical slope we have only two zones, zone number 1 and zone number 3, and this line is the normal depth line as well as the critical depth line. So equation shows that we have the positive values in both the zones, means we always get a backwater curve in both the zones. And you can see, okay, now we will draw a curve which will be neither perpendicular nor tangent, because we draw tangent to the normal depth line and perpendicular to the critical depth line, but here the two lines coincide with each other. So we will get this kind of the curve, the angle in between tangent and perpendicular. Okay, आप इन दोनों कर्व्स को इस तरह से join भी कर सकते हैं, और you can draw them separately. You can draw this curve like this, और ये जो ऊपर वाला कर्व है इसको आप यहाँ पर अगेन इस तरीके से भी ड्रॉ कर सकते हैं. Okay, because you have to show that in both zones we have a backwater curve, and this is the example of the backwater curves. Practical examples: if you have obstruction on a critical slope, then you will get this kind of the curve C1, a backwater curve. The depth of the flow is increasing, and if you have a sluice gate on a critical slope, then again you have C1 behind the sluice gate and C3 below the sluice gate, and you can see there's no hydraulic jump in case of the critical slope. Okay, now comes to the horizontal slope. For horizontal slope, we say that this is the horizontal bed where S naught is equal to 0. If S naught is equal to 0, then according to the Manning equation, Y naught is also equal to 0. Okay, Y naught is also equal to 0. And what will happen if Y naught is equal to 0? It means that, if S naught is equal to 0, then Y naught will be at infinity according to the Manning equation. ओके, मेनिंग इक्वेशन में अगर आप एस नॉट की वैल्यू को 0 पुट करें तो वाई नॉट आपको इंफिनिटी पे मिलता है. मींस इन दिस केस द नॉर्मल डेप्थ लाइन विल बी एट इंफिनिटी. जब आप फिगर ड्रॉ करेंगे ना तो आप कहेंगे हियर वी हैव द स्लोप ऑफ द चैनल बेड, हियर वी हैव द क्रिटिकल डेप्थ लाइन एंड नॉर्मल डेप्थ लाइन इज एट इंफिनिटी. नॉर्मल डेप्थ लाइन विल बी एट इंफिनिटी. और वैसे भी अगर आप जनरली सोचें, अगर कॉन्सेप्चुअली हम बात करें, इफ S naught is equal to 0, it means that there is no effect of gravity on the flow. And remember that uniformity in a flow is due to the effect of gravity. If there is no gravity effect, then the flow will be a kind of non-uniform flow always on the slope. So here you can see that S naught is equal to 0. Y naught is at infinity, means normal depth line is at infinity. So we have only two zones, zone number 2 and zone number 3. There is no zone number 1. Why? Because we have already discussed that zone number 1 is the space above the upper line, and here the upper line is already at infinity. Upper line आपकी infinity पे है, and above the upper line we have no space. So we will say that zone number 1 is missing here. We have only zone number 2 and zone number 3. Okay. So in zone number 2 we have a drawdown curve, and in zone number 3 we have a backwater curve. This is a critical depth line, and you can see that both the curves are perpendicular to the critical depth lines. And here we have the practical example of these two slopes, of these two curves. You can see that here we have a waterfall, so we will get a drawdown curve here, and here we have a sluice gate. Behind the sluice gate we will get H2, and below the sluice gate we will get H3. After hydraulic jump, the flow will again become H2 because there is no normal depth of flow on the horizontal slope. And the last one example is that of the adverse slope. Adverse slope is that for which you can see that this is a kind of an adverse slope where it is rising in the opposite direction. You can see that the slope of the channel bed is always rising in the upstream direction, but here it is rising in the downstream direction. ठीक है, आप अगर ऊपर वाले slopes को check करें, you can see that this is the upstream side where the slope of the channel bed is rises, and here this is the downstream side. Okay, but this is the adverse slope where you can see that at the upstream side the slope is less, the slope is in the opposite direction. Okay, it is rising in the downstream direction. So this is the negative slope. Now again, if you put a negative value for the slope of the channel bed, you will get no value for the normal depth of the flow. Okay? Or you can say conceptually, you will say that normal depth of the flow is at infinity, or you will say that normal depth line is at infinity. So just like horizontal bed, you will say that there is no zone number 1, there is only zone number 2 and zone number 3, and again we have a drawdown curve in zone number 2 and backwater curve in zone number 3. And this is the practical example of adverse slope in the open channel. If you have the adverse slope in the open channel, and you have a sluice gate on that channel, you will get a 2 curve, then you will get a 3 curve, and after hydraulic jump the flow will again become a 2. There is no normal flow on the adverse slope. Okay, so these are all the examples of the water surface profiles in gradually varied flow, how the profiles are drawn in the gradually varied flow and on different kinds of the slopes, and remember that they do not never change. What's the importance of these profiles? The importance of this profile is that, for example, you are going to have a dam on a mild slope. This is the example I'm discussing about this M1 curve. Okay, let's suppose you are going to have you are going to construct a dam on a mild slope. It will be known to you that the depth of the flow will be increased behind the dam. But what will be the increase in the depth of the flow? You will be able to calculate this value by the gradually varied flow equation. dy by dx shows you that what is the change in the depth of the flow with respect to the horizontal distance. So before the construction of a dam, you have to do your paperwork. You must know that what will be the height of the dam, what will be the length of the dam, what will be the width of the dam, and according to that you will be able to calculate the value of dy by dx. You will be able to know that what will be the maximum depth of the flow behind the dam, and according to that maximum depth of the flow you will be able to design the reservoir behind your dam. Okay, so this is similarly, if you are going to construct a sluice gate, for example, on a mild slope, you must know that what will be the increasing depth of the flow. Also, with the help of the flow profiles, once you come to know that what is the depth of the flow behind the sluice gate and how it can be increased, then you will be able to raise. You will be okay. This example or this particular curve or this particular information will help you in designing the sluice gate. Okay, so you must know that all the water surface profiles are used. The importance of water surface profiles or the water surface profiles are computed to for all kinds of the hydraulic structures. If you are going to construct any kind of hydraulic structure in the open channel, you must compute the water profiles, and you must look at the situation there. Okay, there must be no flood situation in the channel because of your hydraulic structure. तो आपने इसका ख्याल रखना होगा कि how much water will be increased. There should be no flood situation in your open channel. Similarly, if you want to raise the level of water by constructing a weir, and you want to divert that water for the drinking purpose or for the irrigation purpose, then you must know you must compute the water surface profile in order to know that what will be the situation and how much you want to raise the level of water and what will be the design of the weir in that case. ठीक है, जितना आपने level of water को increase करना है उसके मुताबिक ही आपका weir भी design होगा. So this is all about the water surface profiles, how they are drawn, how they are computed, and what is the importance of the water surface profile. This is the last numerical problem and the last content of this lecture. You can see at the problem, water is released through a sluice gate opening of 0.3 meter in a very wide and shallow rectangular channel with bed slope of 0.0003 and meaning roughness coefficient of 0.02 at a steady flow rate of 5 square meter per second. Determine whether the hydraulic jump will form downstream, and if so, find the depth before and after the jump. Also find the distance from gate to the jump. Okay, this is a kind of very practical example. In practical example, you can have this situation that you are going to have a sluice gate in open channel and you want to know whether hydraulic jump will form below the sluice gate, and you want to know that what will be the depth of the jump and what is the distance from gate to the hydraulic jump. Okay, these are very practical examples why we are going to discuss all of them. So first of all, we will look whether in case of the sluice gate, will hydraulic jump create or not. If we look at the practical examples, you can see that in case of the sluice gates, hydraulic jump is formed on a mild slope. There's no hydraulic jump. You can see in case of the steep slope, there's no hydraulic jump. There's no hydraulic jump in case of the critical slope. And we have hydraulic jump in case of the horizontal slope and the adverse slope. So there is no situation of the horizontal and adverse slope in the numerical problem because the slope of the channel bed is already given, that is 0.0003, and we know that for horizontal bed the slope is equal to 0, and for adverse slope the slope is negative. So there is no zero value, there is no negative value, means that this is a mild slope. Okay, so if this is a mild slope, definitely hydraulic jump will be created. Let's do this. We know that hydraulic jump will form at the downstream side if y naught is greater than yc, which is greater than y. This is the definition of zone number 3 in mild slope. If you look at zone number 3 of the mild slope, here you can see if you have the depth of the flow here, you will say that y naught is greater than yc, which is greater than y. So if we have this situation of a mild slope, then yes, hydraulic jump will form. Okay, so what we are going to do, if y naught is greater than yc, which is greater than y, then we have the hydraulic jump. The value of y is already given to us. It is given that the opening of the gate is 0.3 meter. This is the opening of the gate, which is equal to the depth of the flow y. So y is given to us, y is equal to 0.3 meter. We will find y naught and yc. Okay, so first of all we will find yc using this equation. Square of q is equal to g into cube of yc, and we will get this value 1.37 meter. And by using Manning equation, we will find a value of y naught, which is 2.86 meter. Now you can see that here y naught is greater than yc, which is greater than y, that is 2.86 greater than 1.37, which is greater than 0.3 meter. Therefore hydraulic jump will form at the downstream side of the sluice gate. It means that the flow is in zone number 3 of the mild slope, and definitely hydraulic jump will form. Okay, what's the second requirement? We have to find the depth of the flow before and after hydraulic jump. Okay, what is the depth of the flow before and after hydraulic jump? You can see that soon after hydraulic jump, the flow become normal. So here, after hydraulic jump, we have the normal depth of the flow. So this is the depth of the flow, and we have already found that normal depth of the flow is 2.86 meter. So we will say that after hydraulic jump, the depth is y2 is equal to y naught is equal to 2.86 meter. We have to find the depth before hydraulic jump only. We will find the value of y1, for which we have already derived this equation in our previous class. So putting the values, you will get this result, 0.527 meter. This is the depth of the flow before hydraulic jump. The last requirement is to find the distance from gate to the hydraulic jump. So for this we will take this gate as section 1.1, and we will take this section just before hydraulic jump as section 2.2, and we will find the distance between these two sections, section 1.1 and section 2.2, for which we have derived an equation in our previous class, that what's the distance between the two depths of the flow, delta x. तो वो इक्वेशन आपने यहाँ पर यूज करनी है, and this is very practical because hydraulic jump is responsible for the erosion of the channel bed. So whenever we know that hydraulic jump will occur, we usually provide an apron in a channel. What is the apron? Apron is actually a concrete lining on the channel bed. So once you know that at this particular distance hydraulic jump will occur, then what you do, you usually provide a concrete lining on the channel bed in order to avoid the maximum erosion of the channel bed. Okay, so if you know that this hydraulic jump will occur at this particular distance, then you will start your concrete lining from that particular distance. And what will be the length of your concrete lining? It will depend upon the length of the hydraulic jump. We have already derived an equation for length of the hydraulic jump in our previous class. You can check it and you can design the concrete lining also. So we have to find the distance. You have to find the distance from gate to the hydraulic jump, for which you will take the gate at section 1 1 and this at section number 2 2. And you can see here at section 1 1 you will find velocity, hydraulic radius, specific energy. Similarly at section 2 2 you will find the same parameters. Then you will find mean velocity, mean hydraulic radius. Using Manning equation you will find slope of the energy line, and then you will use this equation: delta x is equal to E1 minus E2 divided by S minus S naught. S naught is already given to us, and thus we will find that delta x is equal to 40.41 meters. So this is the distance from the gate where the hydraulic jump will occur. Okay, so this was all about our today's class, and this is the end of our open channel course. Inshallah, in next class we will start our new chapter. So is there any question?